Okay. Good afternoon, everyone. Thank you for joining us today for this Lunchtime Tech Talk webinar. Today's Tech Talk is one of a series sponsored by the NJDOT Bureau of Research that include webinars, lunchtime talks, and other events. Tech Talks are meant to share and promote the implementation of research and innovative practices and the transfer of knowledge among NJDOT staff and others within New Jersey's transportation industry. Today's Tech Talk features 3 research studies that we weren't able to include at the virtual NJDOT Research Showcase last October. Like the Research Showcase, today's webinar provides an opportunity for NJDOT employees and others in the transportation community to learn more about the broad scope of academic research initiatives underway in our state. Today, we are pleased to share 3 research studies that dive a little deeper into the evaluation and testing of the performance and durability of materials and pavement used for transportation infrastructure. First, we have evaluating the potential of using foamed concrete as the insulation layer for pavements in cold regions by Dr. Chang Ju of Rowan University creates. Next, we have high friction surface treatment evaluations and alternative friction applications by Dr. Thomas Bennett of Rutgers-Cate. And finally, we have influence of cracking and brine concentration on corrosion and chloride content by Mr. Aaron Strand of the Department of Civil and Environmental Engineering at NJIT. Now, I would like to introduce our moderator today, Mr. Omid Sarmad. Omid is a team member of 2 of the NJDOT Bureau of Research's major programs, the NJDOT Technology Transfer Program, as well as the New Jersey Local Technical Assistance Program. Omid will further introduce today's speakers and moderate the Q&A. Thank you very much, and I hope you enjoy the presentations.
Thank you very much, Amanda. Before we get started, everybody, I just want to go over a couple of housekeeping items on how today's webinar event is going to be organized. Each of our speakers will present their research for about 25 minutes, and then we'll hold for 5 minutes of question and answer immediately after each presentation. To submit a question, please use the bottom right chat box marked Q&A, and please submit all questions to the host. We're going to direct each presenter to answer the questions immediately following their presentation, and PDH credits are available if you stay for the full session. Your name must be included among those who registered today. Also, at the end of the webinar, we'd like it if you could complete the feedback form that should pop up after the event ends. And we're going to try to close out the session by about 1:30 today. So without further ado, let me introduce our first speaker. Dr. Cheng Zhu is an assistant professor in the Department of Civil and Environmental Engineering at Rowan University. Dr. Zhu's research primarily concerns multi-scale geomaterial behavior under multi-physics coupled processes across various timescales for the applications in geological storage, transportation geotechnics, and energy geotechnics. Our second speaker is Dr. Tom Bennett, an associate research professor at the Center for Advanced Infrastructure and Transportation at Rutgers University. Tom's research focuses on asphalt mixture and binder performance, performance-based asphalt mixture design, pavement design and rehabilitation, asphalt pavement forensic analysis, and recycled materials. And our third and final speaker will be Dr. Aaron Strand, a PhD candidate in the John A. Rice Department of Civil and Environmental Engineering at NJIT. He recently defended his PhD dissertation successfully, and he graduated from Oregon State University with a BS in Civil Engineering in 2015. So without further ado, we're going to move on to our first presenter, Dr. Cheng.
Thank you, Omid. So let me share my screen. Oh. All right. Can you see my screen?
Yes, we can.
Okay, great. So let me change it. Okay. All right. So good afternoon, everyone. Thank you very much for coming to this webinar, and thanks NJDOT for organizing this Lunchtime Tech Talk. So I'm Chen from Rowan University. Today I would like to present our research on evaluating the potential of using foam concrete as an insulation layer for pavements in cold regions. So first of all, I would like to acknowledge the support that we have from the Department of Defense Cold Regions Research and Engineering Lab and a number of our collaborators, as well as our internal collaborators at Rowan University. And we also received support from several local companies for providing those materials for testing. So this is the outline of my presentation. So let's start with the background and objective. So as we know, pavement in general, the structure includes a surface layer, base layer, and subgrade layer. So for pavement in cold regions or areas subject to those seasonal weather changes, actually it goes through temperature variations during the winter and summer. So what happens is for those pore water in subgrade layer, which are soil, so during the freezing conditions, those water will actually freeze into ice. And then after the winter, when the spring comes, temperature increase, those ice lands will actually source, so it will cause some weak zones in the subgrade layers. So actually, those weak zones will change the volume and also change the surface layer performance. So as you can see from the right-hand pictures, some of these settlements or surface distressing or cracking will occur. So to mitigate this issue, researchers and engineers have proposed to use insulation layers for subgrade or pavement structure protection under those conditions. And for the insulation layers, currently a number of materials, actually the most commonly used material is the XPS, the extruded polystyrene boards. So as you can see from this UFC standard here. And also researchers have actually tried other materials. The reason is because for the XPS boards, they suffer from several major drawbacks. So two typical ones are first, the degradation of the long-term field insulation ability with moisture accumulation in those XPS boards. And second is that from the figure, you can see that it takes a significant amount of labor and time to actually install those XPS boards in the field. So because all the boards needs to be well aligned with all the joints sealed. So it is actually labor intensive. And alternative materials have been tried, including tire chips, bottom ash, and foam glass aggregate. So we are actually also studying other materials. But in this talk today, I'm going to focus on the one type of material that has not been fully understood for the insulation layer applications. So that is actually the foam concrete. Foam concrete has its own features, including this lightweight and thermal insulation. So the insulation actually comes from the air bubbles embedded in those cement material. And currently, it has been applied for many other applications. However, we want to look at its potential for thermal insulation in the pavement structure in this study. So there are two research problems we want to focus on. One is the potential of using foam concrete as an insulation layer was not well investigated. And second is the methodology of selecting optimum parameters that balance the mechanical strength and insulation effect was not established. As you can see from this figure here, the insulation effect actually will be optimal if the density is low, which means you have more air bubbles in the material. So with more air, actually the insulation effect will be better. And it will gradually decrease when the density increases. And on the other hand, you want to have a high density because the mechanical strength will also increase. So it's actually something we want to look at is to how to balance these two. So here are the research objectives in this study. So we want to look at the relationship between foam concrete density and the thermomechanical properties through laboratory testing. And next, we will develop a thermomechanical coupled finite element model to predict the thermal and mechanical performance of insulated pavements. And we also conduct large-scale testing of foam concrete. So this is a full-scale insulated pavement we construct to calibrate and validate the finite element model. And at last, we perform parametric studies to investigate the influence of different factors on the insulation effect. Okay. So next, I want to show some of the laboratory test results we have. So in the lab, we actually prepared a number of samples with different densities. So we tried 4 different density groups, as shown here. And there are 7 samples per group. So in total, we have 28 samples. And the 4 samples were used for the compressive strength test, and 3 samples were used for the thermoconductivity test. So this is the setup we used for the uniaxial compression test, and that's a thermal conductivity meter used to measure the thermal conductivity of the formed concrete. So the result shows that with with increasing karst density, as you can see, the compressive strength will increase. And that is because of the reduced air bubbles in the concrete sample. And also with a higher density, actually the thermal conductivity values actually also higher density actually thermal conductivity values increase here. So what we want to do is to look at use these two to help us design the large-scale pavement test pavement sections. So in the lab, we actually construct a full-scale soil box, and this is an overview, schematic view of the pavement structure. We have subgrade layer, insulation layer, base layer, and surface layer. And first, we actually we make this soil box, and we put the XPS board as the insulation layers, so which are indicated by this blue color. And then we install those thermocouples to actually measure the temperature in the soil and the pavement section. So the soil samples are actually initially wet, and then we dry the samples. We add the target amount of moisture to reach the optimal moisture content. So next, we mix we kind of mix the sample and compact the sample into the different layers. So actually, we compact the sample and we make multiple layers for the subgrade, and we use this gauge to measure the density, make sure the density actually and water content satisfy our expectations. So we repeat this process for multiple layers, and that's how we prepare the subgrade layer. And then next, we actually add this insulation layer. So insulation layer, after insulation layer, we prepare this base layer. So base layer, again, it is soil, includes target water content. So we have to repeat the process again. And then after that will be the HMA layer on top. So in the end, this is the material properties involved in our test here. So in total, we have surface layer, base layer, subgrade layer, and the insulation material. So here are some of the pictures we have when we build this soil box. So we prepare the soil samples and we compact the soil. So this wire actually is the thermocouple we have to measure the temperature at different depths. And then we compact the layer for each layer, the soil for each layer, and then measure the density for the quality control. So in the end, this is actually the formed concrete we add as an insulation layer. And after that will be the base layer using the recycled concrete aggregates. In the end, we put the HMA layer. So with all the thermocouples connected to the data logger. So this is a picture showing the frost panel we built to create this cold temperature on the surface. And this frost panel is connected to the chiller. So this is the overview of the experimental setup. So we have the full soil box of pavement structure box, and with the frost panel on top, and those are the insulation materials to kind of prevent the thermal insulation from the temperature heat transfer from the surface. And all the thermocouples connected to the data logger. So this is some pictures we have for the temperature change at different depths. As you can see, that green line here is actually the surface temperature. It reaches about -10 degrees Celsius. And in all the different layers, surface layer, top of insulation layer, and middle of subgrade layer, the temperature is actually higher. And especially for the subgrade layer, the temperature is the highest because it is far away from the surface layer, and the heat transfer actually, many of the heat transfer been stopped by this insulation layer in between it. So this result will be used to calibrate the material, the parameters of the FE model. So next, I want to show the numerical model that we have configured. So this model was a 2D symmetric model. We consider the thermomechanical coupled process in this model, and the size is the same as the experimental sample that we did in the lab. So it includes these 4 different layers. And because it's a symmetric, so actually we only used half of the model here. And on top, we also apply a line load to mimic the traffic load. The surface temperature input is actually the same as what we measured from the field. Here are some of the governing equations we used for the multiphysics field, so including the mechanical field, thermal field, and also the hydraulic field. So for the mechanical field, the material is assumed to be viscoelastic for the HMA layer, and the other materials we just simplify to be linear elastic. And thermal field, we consider mainly the heat transfer process. And because it has ice in it, so actually the entire process here, the I indicates ice, and UW means unfrozen water. So actually we consider the 2 phases in the soil, so including both ice and water. And the hydraulic field is governed by this Richards equation. So after we do the finite element modeling, we actually use the output to calculate the pavement rotting and cracking. So the equations that we use actually comes from the NEPDG. So some of the equations are listed here. And this is the calibration that we did to calibrate our experimental results versus using the numerical model. So the numerical parameters are calibrated so that we want to make sure that the predicted temperature at different layer is actually have a good fit with the experimental data. So from there, we can get the mechanical and thermal properties, especially the thermal properties of the different layers. And the next, we performed some parametric studies on using the FE model. So there are 2 groups of studies. One is to study the influence of insulation layer thickness. Another is to study where the insulation layer is installed. So the depth of the insulation layer. So these 2 figures shows the influence comes from these 2 factors. So the left figure is showing the insulation layer thickness. The green color here indicates the insulation layer. As you can see, when the insulation layer thickness increase, the frost depth actually decreases. So this bar chart here indicates the frost depth. With a very relatively thin insulation layer, actually frost depth is larger, and then it gradually decreases. However, for the insulation layer, we can also see that the effect of thickness on the further reduce the frost depth is not that appropriate. It's not that clear. So on the other hand, we also tested the depth of the insulation layer on the results. So as you can see, if we move the insulation layer to a deeper layer depth, so the frost depth also gradually increase, and this is actually meets our expectation as well. So overall, you can see the influence comes from the thickness and the position of the insulation layer. So both of these should be taken into account during the design. So these are the results that we obtained. So actually it's equivalent to the figure I showed just now. So one is showing the rotting depth, and another is, so this rotting depth is calculated based on the NEPDG design. So with more insulation thickness, we see the reduce in the surface rotting depth. And then for this insulation depth, change of the insulation depth, we can also see the remediation effect on the rotting depth. And based on the this cracking, we can actually calculate the maximum allowable traffic. So with a higher insulation thickness, we see a significant increase of the maximum allowable traffic. And here, for the insulation depths, the effect of that on the allowable maximum allowable traffic is not clear, not very obvious. So, which means thickness has a larger impact on the change or on the improvement of this pavement structure to resist the traffic load. So in conclusion, actually, in this study, we look at the foam concrete with different densities, and we constructed this full soil box or pavement structure to test the effect of this insulation layer on temperature change under different conditions. So some of the conclusion we have is that the foam concrete insulation pavement has better performance in resisting frost effect and traffic loading. And to ensure the subgrade layer unfrozen, there is a minimal insulation thickness for foam concrete layer. So in this study, based on our materials that we have, this is actually what the values we get. And if we increase the depth of insulation layer, it will achieve a better mechanical performance and also increase the frozen depth. Using a foam concrete with a higher density it results in a better mechanical performance. So that is all for my presentation today. Thank you, and feel free to let me know if you have any questions.
Thank you very much. We do have a couple of questions for everyone else. I just want to remind you to use the chat box or the question and answer panel if you have any questions. The first question is, what was the estimated design life with foam concrete?
So actually, in this study, we did not check the time frame of the pavement structure, and this actually requires us to do more appropriate lab test or field test using the we have actually the heavy vehicle simulator to study the influence of the real traffic load on the pavement structure. So that's actually something we are working on now. And also another way to do it is to do it through the simulation. So however, in this study, we did not consider that. So yeah, but that's something we want to look at. We are currently looking at, actually.
And were you able to find an optimal thickness and depth combination during this research?
So in this research, we can provide some recommendations, but again, because of the materials we used, the recommendation we have is more specific for the specific materials that we used in this study. And I didn't show here in this talk. We do have a design table that we prepared for the foam concrete material. And if you are interested, we can actually share more information with that. We also did comparison among different insulation materials, including foam concrete, tire chips, foam glass aggregate, and the XPS board. So there are some more information available.
Okay, very good. And I think we have one final question. Was the insulation box that was used to create the sample box replicated in the real-life soil scenario?
Sure, that's a good question. So what we did was we add the XPS boards to kind of minimize the heat transfer. And we want to make sure that if I go back to the slide. So we want to make sure that the heat transfer process, so this is the soil box we used. So we want to make sure that the heat transfer process in this test is actually vertical, along vertical directions. And in reality, the heat transfer, indeed, it may come from the sideways. However, if we look at the larger scale of the pavement section in the field, so when we specifically look at the pavement itself, we usually consider the heat transfer to be along the vertical direction as well. So in the experiment, we installed this XPS board mainly to control the heat transfer and minimize any heat loss around the side boundaries or from the bottom.
Excellent. That's all the questions we have for right now. Thank you very much for your presentation.
Okay,
and we're going to move on to our next presenter, Dr. Thomas Benner.
Okay, thank you.
Good afternoon, everybody. I want to thank the group for allowing me to speak today. As Omi mentioned earlier, what I'll be discussing today is some work that we're doing with high friction surface treatments and some pre-screening tools that we've developed prior to their implementation, but then also looking at some alternative friction applications that we believe could be very useful to not just the state, but the municipalities in New Jersey as well. So if you're not familiar with high friction surface treatment, really what it appears to be here is we're essentially gluing hard angular stone to the pavement surface. This was developed and promoted under Federal Highway's Everyday Counts program. In fact, this was in the EDC2 back in 2014. And the aggregate of choice is generally what we call a calcined bauxite. This is a very hard, very angular stone. It's actually heat treated to increase its hardness. So it's very polish resistant. We use a typical epoxy that's applied to the pavement surface. And then you can see in the upper right picture, the aggregates are placed over top. They're dropped down onto the epoxy and allowed to essentially seat themselves into that epoxy and are glued in. These thicknesses of this material is relatively thin. You're talking less than 1/2 of an inch application. We generally like to see them around horizontal curves where we generally have some lane departure issues. But for in most cases, what we generally see the municipalities and the state using are in declines where there's braking and the horizontal curves. They do significantly improve the friction over what we would generally have as a typical pavement surface. One of the things, though, in selecting, I guess, projects that would require HFST is the pavement condition. And there are some pros and cons of where to use and where not to use. And this is a nice table that Florida DOT put together around 2016 on what pavement conditions are good and what pavement conditions are not good. For example, the not good, we're not going to want to put this on open graded friction course. Pavements with significant cracking or rutting or raveling, areas where we would generally see issues with any sort of bonding to it, like a bleeding pavement, areas that have staining, maybe due to oil spills, et cetera, that sort of thing. However, conditions that we would be a good candidate would be typical dense graded asphalt or typical concrete surfaces. And I have here highlighted pavement conditions rating in good, and I'll explain that in a minute. Areas where there are some examples of polished surface, very low severity cracking, et cetera. The big thing here, though, is that there is a recommendation for a good pavement. And the problem is what defines good. And so when we're talking about selecting or pre-screening pavements, in general, we think of good as no cracking, no rutting. But can we actually have a pavement that appears to be in good condition, at least from a visual perspective, but not be a candidate for HFST? You can see some pictures over here on the right. This is what happens when an HFST section goes bad. The picture on the left there actually shows the transverse location where the HFST stops. And you can see it actually creating a transverse crack in the pavement. More commonly on the right, what you see there is what we would call a shallow delamination, where you actually have chunks of this HFST being pulled up. The fact is that we can actually have a pavement that appears to be in good condition, but not be a very good durable pavement. We have some situations in asphalt where low asphalt contents, high dust contents, excessive production temperatures from the plant, or an overuse of recycled asphalt that isn't used responsibly, you can actually get yourself into a situation where a newly constructed pavement that appears to be good would not be a good candidate for HFST. That picture on the right is a prime example. You can see the two travel lanes there and the shoulder are the same exact mix. The travel lanes there were produced with a warm mix additive back when we were doing some warm mix asphalt trials about 10 plus years ago. The right is conventional hot mix, and you can see there's a very clear difference there in the color. One looks a little bit grayer than the others. It seems to be a little bit more oxidized. And we can get into a situation where these are new pavements, but yet are not suitable. The question is how do we determine whether or not these pavements are suitable? So this goes into some of the initial forensic work that we were doing. And just like most Sopranos stories, our story begins here in North Jersey. We have 2 county roads, and note that the municipalities utilize the New Jersey DOT specification when applying HFST. Both roads were in good conditions. They're very similar in structure. Visual distresses were good. And at the time, a couple of years before the HFST application, they were actually resurfaced. So we have 2 sections that would appear to be in good condition. In 2018, in the spring, we went out to see a couple of locations that had some clear distresses and were noted by the municipal engineers. You can see at the bottom left, there's again another transverse crack that's has initiated at the interface of the HFST and the dense graded. And to the right are some significant delaminations that's occurring. You can even see there's a longitudinal crack right at the edge of the paint that's creating that's initiating, because that's the edge of where the HFST was actually placed. These distresses, these shallow distresses, are typically caused from a couple of things. One, we have a weak substrate. The pavement layer below may be prone to some raveling or cracking. It usually occurs in areas of turning or some extreme stopping, so you have some external forces that are being generated. They are also caused by thermal induced stress, and we'll talk about that in a minute. And it can also be caused by excessively thick epoxy. And the epoxy thickness is very important on this material, because if it's too thin, the aggregates can actually ravel out, pull out, and you're left with just a sheet of epoxy. If it's too thick, the aggregates can actually be seated too deep, and and then you're losing some of that friction. The other thing that happens is that if the epoxy is too thick, due to this thermal cycling, you can actually create a greater stress applied to the surface that can actually pull that HFST off. And that's generally what we were seeing in these sections. So you can see here's Stevenson Ganthier, formerly of New Jersey DOT Materials, now North NJDOT Construction, showing a panel that we found on the side of the road. And that's about a ½ inch thick. And if you look on the other side of that panel, you'll see that that's really the top layer of aggregates and asphalt from that section. One of the major problems with this sort of application is the epoxy that's used is not thermally compatible with asphalt. On the bottom shows what we call coefficient of thermal expansion of different materials, and you can see that the epoxy used with the HFST is anywhere between 2 to 3 times greater than typical asphalt materials. So that means it's going to expand or contract 2 to 3 times of a greater rate than what we would typically get for normal asphalt. Now, if the asphalt is relatively new and is in good condition, we would expect that to able to withstand some of that. But as I mentioned to you before, when we get into some asphalt that may be oxidized, have some higher recycled contents, you may actually be prone to these shallow delaminations, even though that asphalt is relatively new. So what we did is we went back to these sections and we took a very good look at what we're seeing and tried to figure out what we could utilize as a pre-screening tool. What would be something that would be simple, wouldn't require a lot of work, but would provide enough information that we can pre-screen certain pavements prior to whether or not an HFST application would be selected. And so what we did is we looked at a couple different tests. This one is fairly simple to use. This is ASTM C1583. It can be done on a 6-inch diameter core. We make a little bit of a core cut, a pre-core cut into the HFST. You can see in the picture below, through into the asphalt material, and you actually can pull it, and you can see the pull-off strength of the HFST. And it's a test method that's typically used in concrete, especially in tunnels. But what we're looking at it for here is really, can that asphalt material at the top be pulled off? And this would be done prior to the HFST application. This picture here just shows you what it would look like with the HFST. The other thing that we want to take a look at is, okay, well, pull-off strength tells us one thing, but we can still have high stiffness, but materials that are highly aged. And so we're also looking at the asphalt binder properties in the top half inch of the material to get an idea of the durability of that asphalt binder. And there's two different asphalt test methods that we can utilize. One's called a Glover-Rowe parameter, delta T sub C from a bending beam rheometer. And these are fairly simple and routine to run in the laboratory. The nice thing about this particular parameter, the Glover-Rowe parameter, is you can get all the material that you need from really one core if it came down to it. You only need approximately 5 to 10 grams of material to run duplicate, triplicate samples. And it provides you with an idea of the relative stiffness aging of the material. And there's some thresholds that have been developed to determine whether or not the asphalt binder is good. If you have excess amount of material that you can get, you can also run the same level of testing in what we call the bending beam rheometer. This is the traditional test that's used in superpave binder grading for low temperature properties. And what we see here is that we look at this delta T sub C, and that gives us a relative idea of how the relaxation properties of the asphalt binder are being lost, typically over time, oxidation aging, or by use of too much recycled product, shingles or wrap. Both methods work fairly well, but the first method at Glover-Rowe, you require a lot less material to use, so it's a little bit more conducive to very quick forensic type work. Just give you an idea of some of the pre-screening results that we've seen. So we took a look at approximately 8 different sections across the state with varying degrees of performance. You can see from the figure there's 4 sections that were performing well. And there are 4 sections, including those county road sections that I showed earlier, that were performing poorly. And what we first looked at is the pull-off strength. So we look at it and we can clearly see that in the good, it met a certain threshold. In the poor, 2 of them were below and 2 of them were above. So it shows that there's some level of performance there in the field that's related to the pull-off strength, but does not correlate exactly. When we also took a look at the asphalt binder properties, we saw something very similar, where again, what you have is you have in some conditions a very good performance, and in other conditions, it was higher and above. And you can see here in the 4 sections that performed very well, they were all below this threshold. In those 4 sections that performed poorly, they were above the threshold. So this parameter from the binder side gives us a relatively good handle on this general durability of that asphalt binder. When we combine the 2 together, that gives us our best level of performance. And you can see over on the y-axis, you have that binder property. On the x-axis, you have the pull-off strength. And you can clearly see the passing area that you would need for these pavement sections and the failing area. And you could have, as I mentioned earlier, you could have asphalt binder properties that in theory would have enough durability, but might just be too soft and would pull off. Or you can have a situation where the pull-off strength is very stiff and strong, but yet the asphalt binder properties are too stiff and would be poor for durability. So we have this now, this pass-fail area, as we continue to develop and take a look at some of these forensic studies. It does seem to show that this particular area in this performance space does an exceptional job at pre-screening pavements, whether or not we can use this HFST. And again, the major issue here with using the conventional property, the conventional HFST, is the epoxy that's being used. These epoxy materials have a very high expansion and contraction rate when compared to asphalt materials. One of the things in this study was we thought, well, if the compatibility between the epoxy and the asphalt is not very good, are there some alternatives that we could possibly use? And the way that asphalt binders are currently being developed, we can utilize a number of different polymers and methods to essentially create a fairly good bonding agent that is asphalt based. So now we have the compatibility between the asphalt binder and the pavement, or the bonding material and the pavement surface that we didn't have with the traditional HFST. This brings us to Route 68. So this was a section that we had identified as could be a poor performer if we use the epoxy. So what we ended up doing was we had an asphalt binder formulated by a asphalt refinery, and we used that as the bonding agent. The asphalt binder graded out to be a high stiffness over an PG grade of 88, but still met our low temperature PG grades of a -22. So that gave us a good bonding agent that should hold up in the high temperatures that would allow the aggregates to be bonded in place. And because this was a test section, it allowed us to look at different aggregates because the calcined bauxite material is extremely expensive. So if we can use more local aggregates, aggregates that are easier to ship in, or just simply less expensive, that would also provide a cost savings to New Jersey and also the municipalities. So we looked at a local diabase. We also included the calcined bauxite, and we also had a flint rock, which is a very hard aggregate from Oklahoma that we had shipped in. There are some different means that we can actually predict the polishing levels in the field in the laboratory using a device called the Micro Duval, which is a steel cylinder that you put water and small steel shot in with the aggregate, and you abrade those aggregates over time. And then we look at the angularity values in what we call an imaging system, where we're actually taking photographs using computer algorithms to compute the angularity. And on the bottom right, you can see you have different performance of different aggregates. So you can actually pre-screen your materials prior to going out into the field, whether or not your aggregate types are hard enough for these particular applications. Here's just some of the process that we're seeing here. This asphalt binder utilized here actually grades out to what we would call a fuel resistant binder. This is the FAA P404 asphalt material. We did use a warm mix additive in there because what we wanted to try to do is ensure that it was pumpable through their system. So you can see the figure all the way to the left. That's the asphalt binder. That's the bonding system that's being applied to the existing pavement surface. The center photo are the aggregate chips that are being placed. They were spread down to about 14 to 18 pounds per square yard. The picture on the right are the rubber tire rollers that seat the aggregate in place. And then what I don't have a picture of is there's a vacuum sweeper that comes in behind after the roller to clean up all the loose aggregate to make sure that we're keeping obviously the people's windshields intact. It's a very similar and identical process to most chip seals. So it's not very difficult from an equipment standpoint, as long as you have a chip seal manufacturer, contractor in the state, which we do here in New Jersey, except this material we were hoping for to be more compatible than the epoxy-based HFST. You can see some pictures we took of the surface. On the left there is the diabase material. You can see how thin of an application it is. That is, again, that was the diabase material. And the photo on the right is the calcined bauxite. So again, it's a very fine aggregate. It's essentially a one aggregate size, approximately 100% passing the quarter-inch sieve, and provides a very durable and hard pavement surface for safety reasons. With help of New Jersey DOT, we went out to these sections over about a 4-year period. I don't have the latest friction data, but I can show you some of the information that we've collected. You can see here that on the upper right is the diabase, the lane 1. You can see 2018, we were in the 60s. 2020, we came down a little bit into the mid to upper 50s on a friction level. You can see in the bottom right, the calcined bauxite was in the 60 to 70 initial range. That's dropped down now to the mid to low 50s as well. So there is a little bit of a decrease in the friction, which we generally see with some of the HFST. Part of this is due to aggregate orientation, tends to move a slight bit under traffic. But the bottom right, we are also attributing to, there's some bleeding that's occurring on a asphalt rubber chip seal just south of this location. And you can see that some of that binder is tracking over into the travel lanes. And we believe that that's affecting some of our friction results as we're doing some of the testing. We expected about a 10 to 20% drop, but our initial friction values were high to begin with. So we feel that these actually are performing quite well for the application, for the costs, and for the compatibility. The bonding was exceptionally well as well. So we're providing a very good bond between the bonding agent and the existing pavement surface. So in conclusion, what we're finding is that the current epoxy-based HFST, although they provide exceptional friction and work very well for pavement safety, there is a incompatibility between the epoxy-based material that we use to glue down the aggregates onto the road and typical asphalt materials, anywhere between 2 to 3 times. Now that causes a significant problem when we look at our thermal cycling that we generally see in this state, and you get into some of these situations where we had a couple of years ago where one day is down into the upper 20s, 30s, the next day we're up into the 50s. That's a significant change and a significant amount of movement that epoxy is going to go through, and essentially it just pulls off that epoxy from the asphalt below. So to make sure that we're not wasting money, because this is a fairly significant investment that the state and municipalities put forth to put these materials down, there's a pre-screening tool that we believe works fairly well, that you can take a look at your pavements ahead of time to make sure that they're suitable for this epoxy-based HFST. However, what we are finding is that in cases that they're not suitable, there's 2 general options. One, you can go in and mill out that area and repave it and hope that the new material goes down and that's suitable. Or 2, we can look at what we're calling under the New Jersey DOT provisional specifications, a high friction chip seal. And that's the application that I just showed you with that fuel resistant asphalt binder, that stiff high-end binder, and typical aggregates that we can actually get from local areas. That local diabase seems to be very good. We can certainly use the calcined bauxite, but this approach is thermally more compatible, still provides a high level of friction, and we don't get into situations where we see those delaminations. Because quite honestly, what ends up happening is that when you start to get those delaminations, that entire section has to be milled out because there's just no way of patching that area. I want to thank everybody for your time. And it looks like we have approximately 5 to 8 minutes for questions.
Yep, thank you so much, Tom. We have a couple of questions in the queue right now. Let me just open it up. Yeah, and the first one is, what is the life expectancy for high friction surface treatment? Would it be suitable in places with heavier traffic?
Yeah, so that's a very good question. Well, first off, if we're generally dealing with higher traffic, I would probably think that the geometrics of the roadway are designed to not have horizontal curves, to not have these very steep declines where you're going to need very quick braking. But there are some areas in Pennsylvania, some I would say lower volume interstates that have this application on there. The question regarding what the life is, that's somewhat debatable right now. What I would expect it to be more of a function of traffic level than years, because what we're typically seeing is when these things start to hit over the million pass area, we start to see some general issues with the aggregate starting to ravel out. We think that's a combination of some of the UV degradation in the epoxy, but we also do see that some of the aggregate has a tendency to bond. When that happens, I'll tell you, the friction drops off significantly. You go from a very rough angular surface to almost glass. So it's one of the things that we're also concerned with, is that when these applications do lose friction, they lose it very quickly, and you can get a very unsafe area. I don't think I answered that exactly, but like I said, you're really talking applications, yeah.
Yeah. Is there any difference in the noise generated with the use of HFST?
Well, you know, you're always going to get a slight increase in noise when you increase the positive texture. So when you've got aggregates that point upward, that's going to generate more noise at the tire pavement interface. When you create a negative texture, like voids going down into the pavement, you generally reduce the noise. So there is a slight noise increase in some of this. We haven't quantified the exact amount yet, but you would expect there to be a slight increase in noise, very similar to probably what we see in our typical microsurface applications that we have around the state.
And is there anything similar to the high friction chip seal use anywhere else in the country? At
this point, no. In fact, we were one of the first ones to try to push it through. We had to work especially with the asphalt binder supplier. We did a little bit of laboratory work and took a look at some durability to make sure that we weren't going to get initial debonding. At this point, we haven't seen anything specifically targeted like this at particular application. There are chip seals, and chip seals have been used around the country in areas where there are issues with friction, but I wouldn't say that it was specifically designed as a friction treatment like this one.
Right. That is all the questions we have so far. Thank you again very much for your presentation.
Thank you, everybody.
And we're going to move on to our final presenter. Aaron?
Thank you for joining me today as I go over some of the work I've done on the influence of cracking and brine concentration on corrosion and chloride content. Most of this work was kind of some preliminary work for a larger scale specimen. Okay, so kind of the outline of this presentation is I will be going kind of an introduction of kind of why we're looking at bridge corrosion in particular, and then kind of the testing procedure for all the specimens I did, and then looking at the macrocell current results that we collected, and then the chloride profiling results that we collected. So why are we kind of concerned about corrosion? It in a 2002 study, it is an $8.3 billion problem for just specifically highway bridges. And then in reinforced concrete bridges, the primary cause that we see of deterioration is chloride-induced corrosion compared to other types of deterioration accidents such as frost attack, ASR, and carbonation. So for kind of the causes of corrosion of steel and concrete, kind of the three major methods are chloride, carbonation, and dissimilar metals embedded inside the structure. And in chlorides, we'll see sometimes cast-in chlorides, but we'll most likely see surface applied chlorides. That's kind of the focus of this project. So these surface applied chlorides are from road salting typically. And in 2014 in the United States, there was 24.5 million metric tons used just for de-icing of our roadways, which is a large percentage of our total salt consumption. And as the years have gone on, we continue to increase the amount of salt that we use for our de-icing. And for the forms of salt use, it's typically a rock salt or a brine, which is typically about 23%. And that drops it so that we get about -6% or -6 degrees Fahrenheit for our freezing temperature. And kind of a more recent thing from NJDOT is that in the 2018 to 2019 winter, there was about 400,000 tons of salt used, 800,000 gallons of calcium chloride, and then about 600,000 gallons of a brine applied on the roadway just in that 1 year. So what we're looking at is called the macrocell corrosion, and this forms between the upper layer reinforcement and the lower mat of reinforcements inside the deck. And this forms when there's a local anode and a large cathode. And this frequently occurs in chloride-induced corrosion as the chlorides reach the top anodic steel. And in bridge decks, this is accelerated due to that large cathode to anode area between the reinforcement bars within the bridge deck. So there's kind of two different mechanisms that these chlorides can get into it. Typically, we'll see kind of chlorides through the diffusion mechanism, where chlorides need to penetrate the concrete to reinforce to reach the reinforcement. And this typically creates a concentration gradient within it. There's also more of a direct access where the chlorides have a concentrated path reach reinforcement, and this is typically found through cracking of the structure. So sources of cracks that we see in our bridge decks is typically through plastic shrinkage, drying shrinkage, some type of surface tears, typically from finishing of it, flexure and deflection of the deck from loads, and then in other types of single deflection and underlying of any kind of cracks or joints, typically maybe seen in any type of overlays, and then also any type of temperature-related mechanisms. And these type of cracking mechanisms are important because some of these things like plastic and drying and surface tears can be present from basically day one on our bridges. So our governing product of this research was does current testing take into account these real world considerations and the amount of salt placed on the roads, the salt placement cycling of it, and then the integrity condition of the bridge decks specifically. So we were looking at the impact that the salt brine concentration has, as this is likely to vary as the de-icing is probably gone fairly high, and any type that starts to melt will probably decrease in concentration. And how does this type of these levels impact the corrosion within the bridge deck? And also really what is the real impact of cracking and how does it really impact the corrosion time of our bridge decks? So moving into what our testing was. So for our laboratory specimens, we used ASTM G109 for the macrocell current. And in this test method, we assumed there was no initial chlorides in the concrete and that the chloride or corrosion was only from chloride ingress. These mixtures had a design strength of 4,500 psi. And in order to get the amount of samples that we needed, we cast them as two different sets. Set one was 5,600 psi, and our set two was 6,600 psi. And this is due to some issues in the formwork and some consolidation issues on the bottom of some of the specimens in set one, needing a set two to be able to complete our testing matrix. So ASTM G109 has been previously used to study corrosion in steel, as ordinary Portland cement, and also high performance concrete. It's typically been used for surface applied corrosion inhibitors. Also been looked at corrosion resistance of macroalloy steels. In this test method, there's 3 different bars of reinforcement that are embedded into our beam, 2 different cathode rebar on the bottom, and then one single anode rebar on the top. And there's a resistor that's placed between the 2 of them to create the cell. And the de-icing, or the chloride brine is ponded inside of the dam on the top of it. And the sides and top outside of the dam are coated with epoxy, so the bottom is left free exposed to the air. So for our testing, for curing, all our specimens were cured for 28 days in high relative humidity. They were then cured at 50% relative humidity for 14 days before the crack was then induced and the epoxy coating was added. And they were cured for another 14 days at 50% relative humidity before any of the chloride brine testing was started. And the testing involved a 14 days with a salt solution on the top of it. And unlike in ASTM G109, where the data was only collected during the wet cycle, we collected data measurement every 3 days. And then the salt solution was vacuumed off and for 14 days. And then again, data measurement for every 3 days. Obviously 3 doesn't go into 14, so there's a 2-day measurement between the last 2 measurements. And then this cycle was repeated continuously until testing was stopped. So this is what our specimens look like. On the left, you can see what our reinforcement the molds look like, and then when they're all cast. And then in the center right image is what they look like inside of our wet curing room. And then on the right is what the finalized specimens look like with the plastic dams on top for the pounding of the solution. So in order to form the crack inside the specimens, we did a single point load that was applied, and as the specimens were turned upside down, so the surface was on the bottom of it. And they were loaded until 14.5 kits, though the testing was stopped if cracking was observed. And this was done at 5,000 pounds per minute. And through this method, we didn't actually control the crack width, and we did measure them, and they resulted in crack widths between 0.004 and 0.012 inches. And then for the specimens, these crack specimens were randomly assigned brine levels to minimize any bias of a small crack on a small or low brine and a large crack on a high brine, or vice versa. So we used 5 different salt brines, 1.5, 3, 4.5, 6, and 9% sodium chloride solution. The 3% was what is specified in the ASTM G109. We had one uncracked specimen and one flexure cracked specimen. And then again, the current measurements were collected more frequently than specified in ASTM G109. So how we did the data measurement was we measured the voltage across the resistor, and then this allowed us to calculate the current within the cell. And basically the threshold value in ASTM G109 for an integrated macro cell, the current of 75 coulombs. And then if there's a macro cell current greater than 10 microamps, that basically indicates that corrosion was able to initiate and possibly was occurring, but it didn't definitively prove that it was happening. So for the full large-scale Brujac specimen that the laboratory specimens were helping to provide guidance on, it was a 25-foot wide and 50-foot long section, and it was exposed to a 6% brine, freezing and thawing, and also a moving load that went back and forth across the deck. So for this testing, we didn't collect any macrocell corrosion data. We collected the chloride content tested throughout, and so that was done through coring of the deck. So moving into the macrocell current results, this is what the data looks like when it was collected. And we can see that for these, for the 4.5 and the 6% crack specimens, that even on day 3, we were getting values that were above the threshold value, and those are all bolded. And in the uncracked specimen, the values in essence represented any background values between within the measurement multimeter device that we were using. So moving into kind of the macrocell current over time for all the specimens, the dashed lines represent all of our cracked specimens, and the solid lines represent all of our uncracked specimens. And we can see that, that all the cracked specimens up above 3% showed a macrocell current that was above the threshold value. Though it's interesting to note that over time, the 4.5 did start to drop back below the threshold. And this could be due to binding or closing up within the system, not allowing any of the kind of parts to start to kind of penetrate into it further on. And as we got on in testing, we do see that kind of stabilize with the 9%, 6%, and the 3% kind of all in a line of each one of each other in the level of macrocell current. The testing was stopped just shy of 1 year, and this was due to the testing corresponding at that point with the pandemic, where our lab had to shut down, and it didn't make any sense to really restart the testing with that, because the ponding the ponding cycling is what enabled the progressive chloride ingress into the specimens. So moving into this slide, where we can, this is the same as previous, but just kind of showing that the uncracked specimens stayed very much lower than the actual threshold that we were looking for the macrocell current. And this again indicates that at least through testing, there wasn't any corrosion that was likely present within these specimens at the end of testing. So kind of the total corrosion that we measured throughout testing, and we can again see that as time progressed, kind of the corrosion amount kept going up, and we reached the 75 coulomb threshold within about a half a year for all but the 1.5% cracked specimen. The 6% reached at a much quicker rate. This is likely due to that 6% one having the largest crack of the cracked specimens. So kind of some of the findings from all of this is that for cracked specimens, kind of as long as there was kind of a threshold was met if a ponding amount of solution was above 3%, and it reached it at a greatly accelerated rate. And this is kind of what we had kind of figured. But what's interesting is for all uncracked specimens that at all chloride levels, there was no corrosion that appeared to initiate, at least within the 1 year of testing. This was to be kind of expected, as this is a diffusion mechanism, and that does occur over many years. And that the presence of brine was a larger factor than just kind of the brine concentration, as a kind of a 3 times increase in the concentration of the brine didn't result in a 3 times increase in the corrosion values that you were seeing. And there's kind of no difference in whether the current results for the uncracked during our testing time period. Moving into the chloride profiling results. So we used ASTM C1556 for the profile layer depths, and all specimens were profiled until the reinforcement was reached, or in the case of the cores extracted from the deck until the layer of reinforcement as the cores were taken away from the reinforcement. The intervals were for a water cement ratio of 0.4, which is what these were called cast at. And the intervals were kind of 1 millimeter thicker for the cores that were ejected from the deck than what was specified. This was due to the smaller area of the cores, resulting in more powder needing to be able to be collected in order to actually run the test. And we can see in the bottom what the kind of the layers look like as I kind of ground down and extracted the powder from each layer. And then we did acid-soluble chloride testing using ASTM C1152 to determine the chloride content. This is what our profiling setup looked at. We used a Tormach CNC machine. And on the right, we can see kind of what a core looked like during the profiling testing to extract the powder. Kind of kept a tray around the outside of it in order to collect any dust that was ejected from the bit. And on the bottom, we can see one of the laboratory specimens and what it looked like down when it had reached reinforcement. Kind of hard to see in the image, but there was a little bit of corrosion present at the reinforcement in the cracked specimen when we had reached the reinforcement. So for the titration process and setup, we collected the powder sample for each of the layers, and then we used a nitric acid solution and boiled the powder inside the solution in order to extract the chloride from it. And then the solution was then filtered, and then we used a titration setup in order to determine kind of the equivariant point of it, and that allowed us to figure out the amount of chloride per based on the percent based off the chloride content based off the amount of concrete percent. So for the laboratory specimens chloride profile, we can see that there was an increase in the amount of chlorides as the amount of chloride concentration was increased for each of the specimens. But what's interesting to note is that near the surface for most of the specimens, that we did notice that the uncracked and cracked specimens did have fairly similar values, though at the depths that started to get closer to the reinforcement, the cracked specimens continued to have a much higher level of chloride content than the uncracked specimens. And at the near the reinforcement, the cracked 1.5% brine ended up actually having a higher chloride content than the 9% uncracked at this depth, indicating that the presence of the crack is very highly likely to increase the amount of chloride that we can see in it. So for the core samples profiling, basically we saw that within a couple months of starting the testing, that we did see a fairly high amount of chloride within the testing. It was interesting to notice that as the timing of the testing continued, we did see kind of lower amounts of chloride, but this is likely due to the fact that the cores were all taken from different areas of similar but different areas of the deck, and just kind of the natural variations in the deck may have likely caused the amount of chlorides to change. And also too, that for most specimens that more near the midspan, we did see typically a slightly higher amount of chloride than we did in the more the fixed ends at the end. This is likely due to the moving load on the bridge deck causing a greater increase in the chlorides. Again, this is a combination of all the data where we can see that the comparison between laboratory specimens and the field specimen. And the laboratory specimens, especially in the cracked ones, do show a fairly high amount of chloride within them compared to the real specimen. So this is likely again due to the fact that we induced a crack versus just kind of what was naturally occurring from the actual finishing process and curing process of the deck. These are the diffusion coefficients that we calculated from the data that we collected. And what's interesting to note is that we do see a fairly drastic increase in the amount or in the diffusion coefficient for the cracked specimens compared to the uncracked specimens. And then also for the cores detected in the deck core, we see a fairly high amount of chloride diffusion within the specimens that we tested. What was, I think, one of the most interesting things about this data is that when we did the curve fitting in order to figure out the diffusion coefficient, that for an uncracked specimen, the curve fit fairly well as to be expected. And in the crack specimen, where we have kind of the dual mechanism within our powder of the diffusion from the top and also kind of out from the crack, and then also from the crack itself, the curve fit is not very well aligned with the actual measured data values, indicating that when we start getting into crack type situations, that other methods might be needed in order to figure out the amount or to figure out the kind of diffusion coefficient, or how the chlorides are actually ingressing into it, as kind of the more typical diffusion coefficient isn't likely to be as applicable to these situations. So kind of from our chloride content, we found that the chloride content was greater in lab specimens, especially when they're subjected to higher brine concentrations, and that a similar chloride content was found near the surface for the cracked and uncracked specimens, though this was greater in cracked at depth. And the similar coefficient of diffusion was similar for all uncracked specimens, and this makes sense as at the end of testing, none of them had shown any amount of corrosion or amount at that point. And then the apparent coefficient was greater for all tested crack specimens, and again, this makes sense as the amount of chlorides can penetrate much quicker. But again, this chloride profile fit show that this might not actually be fairly actually representative of what's actually occurring. And then the det chlorides show high chloride ingress at very early testing times, and again, the chlorides are taken from several different locations. So from this work, there's kind of three different ongoing type of projects within our research group. One of the testing is looking at other concrete mixture designs, and then also other types of rebar and how those types of things impact these results. And also from some of this data, we're kind of working on developing a model. One of the other researchers in our group kind of looking at specifically how to kind of model the amount of chloride content and then the corrosion current specified within these specimens, maybe give a better insight into the chloride content of what's actually occurring. Thank you, and I can take any questions now.
Thank you very much, Aaron. We do have a couple of questions. This one came in a little earlier, and I think you did go over it, but just to be sure, the question was, among the crack samples, did the higher brine solution show faster corrosion / what was the rate?
So since they all really showed the cracked ones, other than the 1.5, like it showed, at least in the macro cell, basically almost immediately for all of them. Kind of the rate of it, not as much. Going back to kind of the total corrosion, the 6% did show a quicker rate and reached that threshold quicker than the other ones. But the other three all were about kind of the half years where they all kind of cross the threshold. So there might be an increase in the or decrease, I should say, in the time to chronic corrosion as the chloride or the brine is increased, but it's maybe not as much as would be maybe expected from such an increase.
Okay. And did you attempt to introduce temperature as a variable, or do you see that as part of future research, perhaps to do a freeze-thaw cycle?
That would be part of kind of for future research. And one of the other questions that we can talk about in this part of this work, we did look at doing some type of freeze-thaw work on kind of the concrete itself, but not with kind of the actual cycling of the brine. As a part of kind of that different mixture design, one of the other members of my research group is doing some, I think, like kind of salt scaling type work, but more actually looking more like temperature would be something that would be kind of interesting to figure out how that would play a role into the rate of the ingress.
Great. And how would you like to see your research findings be used to inform bridge design, operations, or maintenance in the future?
That kind of a lot of the testing that we do is more kind of like it shows how maybe mixtures might perform against each other, but for actual application based work where things are really important, we need to be more careful about how we select things, and actual like testing of our materials for these type of things are important, and especially incorporating the amount of cracking, and also from just kind of literature review, the change in brine concentration. Like I was doing stuff at 1.5 to 9. A lot of other brine solutions are up, can be up to 23% chloride content. How that content might impact it, because there's very, very little about that change and how that impacts things.
Okay, I think that's all the questions we had here today. Thank you very much, to you and all of our presenters today. Thank you very much for Tom, Cheng, and Aaron. All three were wonderful presentations. Just to let everybody know, the presentations will be posted on the Tech Transfer website at njdotTechTransfer.net. We're going to be sending out a notice to everyone who registered when the presentations have been posted and how to access the certificates. Also, please be sure to fill out and submit the survey for today's event. It should be available after the webinar is closed. Thank you again, everybody, and stay safe.